Okay, so we're given a function here, and they say right up at the top that this function is y equals x plus 1, so it's a nice straight line. And then they talk about the integral, meaning the area under that function, starting at -2 and going up to a stopping point to be determined later. So we're beginning at -2 here, and we're counting area, negative at first, then becoming positive, and we keep going and keep going and keep going until at some point, x, which they'll tell us later, we're going to stop adding up the areas. So we can use this integral to figure out what that area is going to look like. It's the integral, they say, from -2 up to an x we'll get later of our function, which is simply x plus 1. Or, sorry, I was going to write x plus 1 dx, but it is a little weird to have the same variable in your integral that you do in your limit of integration. And to avoid that, we use what they call a dummy variable, where we just change up the letters on this. Call this a plus 1 dA or t plus 1 dt or whatever you like. I guess they use t's. I'll go with that. I don't mean to weird you out by changing the letters, but the point with a dummy is that you really can use any letter because it's about to be replaced by either -2 or x in a few seconds anyway. So the letter that you choose here is not critical. So we do an antiderivative as we have been taught. The antiderivative of t is 1/2 t squared. The antiderivative of 1 is t. And we evaluate that from -2 up to x, whatever that is. So when we plug x into this, all that happens is some letter switching. We get 1/2 x squared plus x minus, and then we plug in -2. So we get -2 squared is 4, half of that is 2. And then we get plus -2. So 1/2 x squared plus x, and 2 plus -2 is 0, so isn't that nice? That entire second term just drops out. And 1/2 x squared plus x is our cumulative area, meaning if we give you a stopping point, a right edge for this area, you can plug it into here and that'll tell you how much total signed area has built up. Now they say determine the value of p of -2. This is a trick question. Do you remember this? We've seen this before. This will come out to 0, and maybe you remember why. The idea with this is our integral is already designed to start at -2, and now we're saying it should also end at -2, meaning there's no width here, and meaning that means the area should come out to 0. Let's see if it does. Let's see if this function actually works. If we put in 1/2 of -2 squared plus -2, -2 squared is 4, half of that is 2, plus -2 equals, yep, good. Our function's doing what it's supposed to. It gave us 0 there, just like we knew that it should. So you can see it coming very easily if you are paying attention, but even if you aren't, this function will save you and say, yeah, the total area there is 0 because you didn't give me time to accumulate any rectangles. If we do p of 3, now we're going out to about there. We're adding up all this area. It looks to me like we'll get a small amount of negative and then a large amount of positive, so we should get a positive result. What do you get from p of 3? 3 squared is 9, half of that is 4.5, plus x is 3, total area of 7.5, or 15/2. So that's believable. And, now this one's fun, p of -3. That means we're starting at -2 here, and we're going out to -3 this way. Now, careful. What sign do you think this result's going to have? This is tricky. There are two things to consider. First, the heights here are negative, which means we're thinking negative result, but also we're integrating from right to left, We're starting at negative 2 and going to negative 3, and that means we're going to get negative widths also. So those negatives should cancel out, and I bet you we get a positive result when we do this. Negative width times negative height gives positive area in the weird world of the definite integral. So let's put negative 3 into this and see what we get. 1/2 of negative 3 times negative 3 is positive 9 plus negative 3. That comes out to 4.5 minus 3 is positive 1.5. So two negatives, or a negative height and a negative width, can give you a positive area when you're integrating. Doesn't come up real often, but nice to know.